So now we're going to talk about a very important concept to gases, and that's going to be something called the ideal gas law. Okay, so let's look at the ideal gas law. The ideal gas law is going to be PV equals nRT. That's the equation for the ideal gas law, where P is the pressure, units of that have to be atmospheres, V is the volume in liters, T is the temperature in Kelvin, N is the number of moles of the gas in moles, and R is going to be a gas constant. It's always going to be the same value. Now when looking at this, you have to keep the units correct. Okay, you have to use atmospheres, liters, Kelvin, and mole for the units, otherwise this equation doesn't work. The reason for that is because of the gas constant. When we look at the gas constant has a value of 0.08206 atmospheres times liters divided by moles times Kelvin. Okay, so if you don't have the proper units, you're not going to cancel out the appropriate units. Now this ideal gas law came about from observations by a variety of different scientists. They did various measurements with gases and under different conditions, came up with these theories, put them all together, they ended up with the ideal gas law. So this ideal gas law is going to be a combination of Boyle's, Charles, Avogadro's laws. But we don't need to know what Boyle's law was, what Charles's law was, what Avogadro's law was. What we need to recognize is we need to understand the ideal gas equation and derive those from it. All right, and this is what I mean by that. If I take PV equals nRT, so if I'm going to have constant pressure and number of moles, then what we need to do is look at that PV equals nRT equation, and what we want to do is derive a new equation where everything that can change is on one side of it and everything that's going to remain constant is on the other side of it. Okay, well, if P and N are constant, R is always constant too, so let me rearrange this equation. My N, R, and P are on one side of the equation. They're constant. My volume and temperature are on one side of the equation. They could change. So when I set this up, volume 1 over temperature 1 is equal to NR over P, and NR over P will be equal to volume 2 over temperature 2. Okay, where volume 1, temperature 1 are our initial starting conditions, volume 2, temperature 2 are our final conditions of our gas. So those ratios are both equal to the NR over P because NR over P is going to remain constant. It's not going to change. That value is going to stay the same no matter what we do those conditions. Okay, so what we can end up doing is get a new derived equation. So under constant pressure and number of moles, volume 1 over temperature 1 is going to be equal to volume 2 over temperature 2. Right, so now how does that apply to actual gases? Well, keep this equation in mind. So an example of this is a hot air balloon. So how does a hot air balloon work? Well, as you heat up the air inside the balloon, it starts to expand. It starts to occupy a larger volume. We haven't changed the number of moles of gas inside that balloon, and we haven't changed the pressure inside that balloon because it's based upon atmospheric pressure. It's open to the atmosphere. All we're doing is heating up that gas. So as we heat up that gas, increases in volume, because it's got the same amount of gas over a larger volume. Well, mass over volume is density. So if we increase volume, don't change mass, we decrease density. So it becomes a lower density than the air surrounding it. So it starts to float. All right, that's the basics of it. But it comes back to this ideal gas law and this relationship between volume and temperature. All right, so let's look at using this in a calculation. So let's say a gas for a balloon has a temperature of 26 degrees Celsius or 299.15 Kelvin, and the volume of that gas initially is 30 liters. What's the new volume going to be when we heat it to 500 degrees Celsius or 773.15 Kelvin? Well, we can look at this V1 over T1 equals V2 over T2 relationship. So plug those into the equation. We want to know our new volume, solve for V2. We get it to be 57 liters. Okay, so that's a relationship under constant pressure and constant number of moles. All right, what if we have constant temperature and number of moles? Well, I get everything that's constant on one side of the equation. It's going to be in the bold here. So the N, the R, and the T are all constant. So pressure and volume could change this time. Okay, I've got the P1, V1 equals nRT which is equal to P2V2, which means then that my P1V1 is equal to P2V2. All right, so let's look at an example of this. Remember, I'm under constant temperature and number of moles, so P1V1 equals P2V2. Well, if I look at this picture here, as I go from a volume of 1 liter at 1 atmosphere, if I decrease the volume in half and go to 0.5 liters, now I would be at 2 atmospheres. So my P1 is 1 atmosphere, my V1 is 1 liter, my V2 would be 0.5 liters, and I could calculate my P2. Right? What does it mean? Well, as I decrease my volume, my pressure is going to go up. As I increase my volume, my pressure will go down. If I increase my pressure, my volume will go down. If I decrease my pressure, my volume will go up. Okay, they're inversely related to each other. All right, let's look at a little bit more practical application of this. When we look at scuba divers, they use pressurized tanks of air. Well, why do they use pressurized tanks of air? Well, if I look at a scuba diver starting at a depth of 0 meters and a pressure of 1 atmosphere, okay, so that's where they normally can breathe at, no problem. All right, well, as the scuba diver goes further and further down, they actually start to feel a pressure on them from the water surrounding them. The water starts pressing down on them. Well, now the pressure they feel can be equivalent to 3 atmospheres externally, what's pushing down on them. So now they need to overcome that pressure when they try to breathe in. If they want to draw air into their lungs, they have to overcome that pressure to breathe in that air. Well, if the air inside the tank isn't a higher pressure than the surrounding pressure on the body, you'll never get that air forced into your lungs. Remember when we talked about breathing, you decrease the pressure in your lungs, the external pressure forces the air into your lungs. All right, well, if you don't overcome that pressure of 3 atmospheres, somehow you can't breathe. So the way they overcome it with scuba divers is they pressurize the air tank. So they make the external pressure a lot higher than what the scuba diver would be feeling. All right, let's look at another equation. So constant volume, constant number of moles. Everything is constant on one side of the equation. So I end up with P1 over T1 equals P2 over T2. Okay, so let's look at an example of this. If I take a tire that's full of air, all right, what's going to happen to the pressure in a tire when it's cold outside? Now, keep in mind it's a fixed volume. The volume of the tire isn't changing. The amount of gas you have in there isn't changing, unless you add or remove some of the gas, but we're not doing that in this case. All right, well, if you look at the pressure of a tire when it's cold outside, the pressure inside the tire will actually decrease. So as it gets cold outside, the molecules of gas get slower and slower. They hit the wall of the tire with less force, and thus our pressure is going to decrease. Okay, now a question to ask yourself, why shouldn't you fill your tire with air when it's cold outside? Well, if you fill your tire with air when it's cold outside, you're putting in a certain pressure inside that tire. As it warms up and gets hotter and hotter, that pressure is going to go up as well. Okay, so you're going to end up with a higher pressure than you should inside that tire. All right, but that's looking at the relationship between pressure and temperature. All right, what if we have constant pressure and temperature? Well, get everything on one side of the equation that's constant. Get our relationship, so V1 over N1 equals V2 over N2. All right, what does this mean? Well, real simply, it means if I have more moles of gas at a constant pressure and temperature, it's going to occupy a larger volume. So think about when you're filling up a balloon. As you blow air into a balloon, what happens? Well, the more gas you put in, the larger volume it gets. Okay? You're just adding more moles of gas as you breathe into that balloon. Okay, so with all these relationships, be thinking about that ideal gas law. Be thinking about looking at what conditions are constant. Let me rearrange this equation. Let me put everything that's constant on one side of the equation, and then I can set up my initial and finals equal to each other. Now, if you want, you can go through and memorize all the different forms of the equation, but this is a lot easier. This will apply to a lot more problems. All right, one last thing to talk about with ideal gas law before we get into some calculations. Something called standard molar volume. So, under standard conditions, under standard temperature and pressure, 1 mole of any gas is going to occupy 22.4 liters. That's the volume it's going to have. So it doesn't matter what the molar mass is of the gas. All it matters is if we have 1 mole of that gas at STP is what we call it, standard temperature and pressure, it's going to occupy that 22.4 liters. So you need to know that STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, pressure is 1 atmosphere. At 0 degrees Celsius and 1 atmosphere, 1 mole of gas, 22.4 liters is the volume it's going to have. All right, so let's prove it using the ideal gas equation. Well, if I plug my 1 atmosphere pressure in, I'm solving for my volume. I know I have 1 mole of gas. R is constant, so it's that 0.08206 liter atmospheres per mole Kelvin, times my temperature in Kelvin. If I solve for V, I get 22.4 liters. Okay, so when it comes to these gases, it's only concerned with the moles of the gas. As long as you have equal number of moles of gas, you're going to have the same volume or the same pressure if everything else is kept the same.